So on this script, make sure to just highlight after that hashtag in order to read in the data file. If you just try to run that line, it's commented out. It's not going to work. Set it up like I did the last one as far as having, I just put in a variable called unit4 filter to try to make things a little bit easier. And then I went ahead and I am subsetting the making a PCA data frame that is just like the 19 variables that we're going to be working with. And throughout the course of this particular lesson, it'll become very apparent why, like, I'm just subsetting that as a separate data frame instead of using the select function every time we need to call this. But that said, these first two problems here, what's
Austin, sorry to stop you. This is Elise. I'm getting an error when I try to run the PCA DF one with the just those variables.
Did you run or did you load a tidyverse?
Yes.
And is your data frame showing up in your
environment? All of that worked fine. It just says error in select unused argument. Then just the parentheses to scrim 101.
I have the same error.
Okay.
I wonder if there's a way for Elise to share her screen.
Maureen, you said you're having the same issue? All right, do this. Restart R. If you go up into session and click restart R, and then load tidyverse, but only tidyverse. Don't load those other libraries yet.
Okay.
And then try to run it again.
This may take a minute. You can keep going.
And it worked for me.
Okay. Did you happen to load these other libraries as opposed to just the three that I had up top?
Yes, I did.
That's why I specifically did not, because there with this paran especially, like if you load, if I come up and load paran, it's going to tell me right here that it's masking select. So the reason it wasn't working is because when you put select here in PCADF, it thinks that you're saying paran select, not dplyr select. So that's the reason that I explicitly call that later as opposed to calling the library itself.
Okay, sorry about that. It's working now.
So quick roll call then. Is anyone else struggling to get to the point where we've called in the libraries, called in the data, and created the subset data frame?
No.
No problems.
Okay, excellent.
All good.
You guys are awesome. Okay, so I think I'm just expecting everything to just crash, so I'm like thrilled that it's not immediately going to shit here. Okay, let's start with our very first homework question then. Is that right, Austin? Are we ready to do that? Okay, and I want to walk you through a little bit about what we're doing in class. Now, the homework says you need to download a program to run parallel analysis, and that's not true if you're using R, because R already has this integrated. That is only true if you're using SPSS, okay? So if you're using SPSS and you want to run PCA, you can't run it within the program, so I gave you a link to a small program that will run it for you. All right, in this homework, we're going to be running a series of PCAs and EFAs and practicing different kinds of rotation, oblique and orthogonal, with our data set, and we're going to be looking specifically at the individual items that comprise the scales of discrimination experiences, the Rosenberg self-esteem scale, and the depression questions. If you remember that these are items that we have used as total scores in some other analyses, like in the LR assignment last time, we were trying to predict depression 2 from depression 1 and self-esteem 1 and discrimination 1 and all these other things. But those were total scores. We had already summed or averaged the self-esteem, the 10 self-esteem items. We'd already summed or averaged the 4 depression items, and we'd already summed or averaged the 5 discrimination items. So we're really going backwards in terms of like what order things should be done. And we're starting off by saying, was it a good idea to put all those items together into one score and call it depression at time 1 or self-esteem at time 1? That's what our lab is going to be focused on, is like the integrity of those total scores. And the reason that Austin wanted to create this subset of data is because we're only looking at the time 1 just for illustrative purposes, and we're only looking at those 19 variables, 5 discrimination, 10 self-esteem, and 4 depression. And we want to basically keep them in their own data set because it's going to be a lot less typing for us later if we have it that way. So our first question asks about the nature of variables appropriate for PCA and EFA. What are the kind of variables that you need in order? What's the minimum data set?
You need multiple continuous variables, and your slide says 5 to 6 per factor, but I'm not sure, like that doesn't exactly make sense to me because you don't know how many are gonna, like how many factors you're gonna have. So I guess that basically means like kind of a lot, or if you have a bunch of concepts in mind, you might have like 6 variables per concept in mind.
That is a perfect answer, and it's also a perfect question. So if you remember, at the end, once we're all done with our analysis, how many variables do we want to have loading significantly or marking a component or factor? How many?
Like two or three?
Yeah, we'd like to have like 3, right?
Mm-hmm.
It would be great if we had 3 that were really like, I belong on this component or factor. Well, obviously we're not perfect, and we don't know on the front end exactly which 3 are going to be the best ones. So when you are typically doing this, which is in the context of scale development, you typically want to start with at least twice as many items as you ultimately think we'll end up with, which is why the minimum data set says, try to put at least 5 or 6 that you think are all going to end up together, because they may not. And so if you're needing to trim some later, if you've started off with more than you needed, then you can cut variables away, but you can still end up with a well-defined component or factor. Does that make sense?
Mm-hmm.
Okay, awesome. Any questions about that first one?
It reminds me of EG, ERPs, like you have a whole bunch of electrodes and then like you can get rid of the ones that don't work.
Exactly, yeah, for all of you brainy folks. Yeah, you take a bunch of measurements because you're not actually sure in an individual person or for a particular task, which ones are going to be the ones that are best indicating what activity is happening. And so getting more channels is a way to make sure that you've got those things well measured, because you might not use all 64 or 128 or however many you use. How about the next question then? Next question asks about assumptions. So let's hear from some folks who maybe haven't chimed in yet about what are some of the assumptions that are made in PCA or some that might be unique to EFA.
The variables have to be really highly correlated.
Good.
And you need a really large sample size.
Good.
Also, missing data needs to be random. And we want to use estimation techniques, but ones that don't reduce variance if we do have missing data.
Absolutely. We have to be really careful not to provide missing data estimation techniques that distort the nature of our correlations.
I can keep going, but I wanted to give other people
Yeah,
an
let's hear from some
opportunity.
others. Thank you, Isabel. How about from someone who hasn't chimed in yet?
It can be really sensitive to outliers among cases for someone that doesn't fit.
Yep. Very good. What else? Dulce or Nia?
In my notes, I have the higher the correlations, the better. And for PCA, multicollinearity isn't a problem.
Perfect, yes. It's like the only time all semester where we're gonna say multicollinearity doesn't matter, but it only doesn't matter for PCA. Okay, anything else? There are a couple more.
How much this factorability of the correlation matrix?
Yeah, we're gonna test that assumption in a little bit, but you need to make sure that your correlations or your set of X variables actually have some underlying factors that could be extracted, right? That somehow they do cluster together into these components or factors. Did we miss any?
I don't explaining anything.
Exactly.
Anna,
Yes.
I am confused about the outliers among variables and then the outliers among cases.
Yes. So there are individual people for like individual participants for whom maybe the structure doesn't hold. So for instance, it may be that in most people, all of these depression items kind of co-relate, but then there might be a person who has some unique symptom of something that it doesn't hold for that person. So you would find that a single person is an outlier the same way that a single person might be an outlier in all the other analyses we've done. And that would be a person who maybe needs to be deleted from the data set. So if you're running any study and you have one person who just really doesn't fit a pattern, they're not answering the same way, their brain isn't working the same way, whatever, that would be the outlier among the cases. The outliers among the variables is what we talked about a little bit ago, which is a individual variable in your data frame that doesn't seem to go with all the other ones. So for instance, in our data, we have 19 variables. We might end up with a variable or two that really doesn't seem to have anything in common with the other ones. And that would be an outlier among the variables. It doesn't actually load onto any one component or factor. So
I have a question about linearity. I don't know if someone said that and I just missed it, but don't we assume linearity too?
yes, we do. Basically, any assumption that relates to the integrity of a correlation is going to apply to factor analysis in PCA. So fundamentally analyzing the relations among variables. So if two variables are not linearly related, if they're sort of curvilinear, kind of like anxiety and performance, if you have that situation, then you're going to have a distorted correlation. The relation between anxiety and performance might actually be described as like no relation from an like a correlation perspective. but that's because it curves. Like more anxiety increases performance up to a point, and afterwards it really starts to decrease performance. So if you were to take the average, on average, it might be that it's like a 0 correlation, but that's not right. So anytime you have two variables that are not linearly related, but that seem to be related in this curvilinear fashion, then you're violating the essence of linearity. PCA and ESA assumes linearity because everything has to be captured with a correlation. So everything that applies to an assumption about a correlation is going to apply to PCA and ESA. Does that help, Casey?
Yes. Sorry. Starting it to the other screen.
Okay, Austin, I think it's at you now.
All right, so looking at the correlation matrix here, gonna show you a few different things that we'll be using throughout this particular lesson. Because first, obviously, if we're just wanting to check a correlation matrix of our PCA data frame, you know, you have core. And, you know, when you're looking at multi-collinearity, you're looking for those high correlations, but obviously this makes it kind of difficult to sit here and look through a 19 by 19 matrix of numbers. So instead, we can simplify this a little bit a few different ways. One is with a function called lower mat with a capital M. And what this will do is basically just give you that lower matrix for the correlation matrix. So we'll be using this throughout, and later we'll see this. And then as far as, well, one thing I want to point out is I want to make sure that everybody's tracking on what it means if we say to like wrap something in R. So there I might say just wrap your correlation in lower mat. And so what we're saying is put like everything that you have inside this other function, wrap it in this other thing. So here in this case, you know, for instance, as far as like getting an answer for what is our highest correlations here, because basically if we're looking for multicollinearity and we're saying like, all right, let's see if any of our correlations are greater than 0.8. Sure, you could sit here and manually look through even this lower matrix, but you can simplify that a little bit more by, you know, sorting those. So if we wrap that in sort and we tell it decreasing equals true, it will now give us those correlations, but instead we'll just output them in decreasing order. So we can see that our highest correlation is 0.69 out of all of these correlations.
I want you to pause for a moment. I don't know if are you guys able to see his syntax, his typing okay?
Yeah.
Really small, but it's working.
It's a little hard for me to see, but again, I have a tiny screen.
If I zoom in a little, is that a little bit better zoomed in?
Yeah, that's much better. Yeah, that's better.
Okay.
Okay, so let's pause for just a moment. I want to make sure that we're all giving ourselves time to actually run that. And so Austin started by just doing core parentheses PCA.df, which gave you the regular correlation matrix. It's unreadable, right? So the next thing he told us about was how to use the lower mat, which is lower mat is the lower half of the matrix, right? Correlation matrix is symmetrical. There's ones on the diagonal. So we only need to display half of the matrix in order to get all of the information. And I assume there's an upper mat function, but it's the same thing, right? Because it's symmetrical. So by doing lower mat, then parentheses, core, parentheses, PCA.df, paren, that allowed us to just see that really beautiful, simple correlation matrix. And it also automatically rounded it, I think.
It does.
Yeah, it's so pretty. It's like so much easier to read. And so you could, as Austin said, just you run that and glance and see your correlations and say, well, do we have things here that are correlated? Is everything a 0, or do we have things that are higher than 0? But the next question we have is, if we run an EFA, we want to make sure we're not violating the assumption of lack of multicollinearity or singularity. So we need to look at our highest correlation to make sure that we're not going to run into problems when we do a matrix inversion. So the final thing that Austin did was he taught us how to sort the correlations in a matrix by size. So that they started by using decreasing equals true. It would start by giving us the highest correlation, and then it would list all the correlations in order from highest to lowest. So all we need to do is look at the first correlation.
And then the last piece to this, because also throughout we'll want to be rounding things, is now to take everything that we have here and just wrap that in round. And then come to the end, add a comma, and if you want to round it to 2 digits, then you just at the end add a comma 2, and it'll round that. If you want to make it 3 digits, just use that round to 3, etc. So that round function is something that we'll be using a lot this particular assignment as well. So just again, just think of these as piecing together from the basic components. The core of this is this correlation function that gives us that correlation matrix. Lower mat strips that down so that we don't have 2 of every value. Sort just puts them in decreasing order for us, and then rounds it down to however many digits we're looking for. Any questions there?
No.
So how do the correlations, how do the correlations look then? As
Yeah. Basically, what you're wanting to look for, just like in the other analyses that we've done, you know, if your correlations are above 0.8, you might be looking at some issues. But in this case, our highest is 0.69, so we're good here.
Let's pause for a moment and make sure. You know, maybe either say it or maybe type it in the chat box or something if you're like good to go, like you're able to run this part, you got everything you needed.
Good.
I'm good.
So I have one quick question. So you want it to be kind of high, but not above 0.8 is what you're saying?
Yeah, you want them to be high. In PCA, it doesn't matter. They could be almost 1. But in EFA, it does matter. You are inverting a matrix, and so you have to avoid multicollinearity or singularity. So we start to get nervous at 0.7, and we really have a problem at 0.9. And so conventionally, you might say like correlations above 0.8 or might introduce problems for us. And it looks like people are good. We're correlating everything with everything here. All the variables that we're going to throw into our PCA or EFA.
All right, and so then on number 4, we're looking at the KMO, the Kaiser Meyer Oslo,
I think.
Oh, whatever, the KMO value and Bartlett's test of sphericity. These are just 2 simple, straightforward functions out of the PSYC package. So I'm going to call it out this first time that we use it, just to give you the reminder of where these functions are coming from. And as far as like getting that KMO value, it's literally as easy as saying KMO PCA DF.
And so what are we checking here, guys?
This is Anna, because I can't turn on my mic without feedback, but you run the tests to let you know if your factors are related enough to run an analysis on it?
And this is the assumption of the factorability of your correlation matrix. So that's right. This is testing the assumption of factorability.
There we go. Sorry, I'm trying to get the actual Word document pulled up here. All right. And so then for as far as the Bartlett's test, so with this KMO thing, what the actual statistic that you report is this overall MSA. So in your homework where it says like, what is the KMO value? Your KMO value here is 0.85. For Bartlett's test of sphericity, that's where you're going to pull your p-value from. And again, this is from the PSYC package, and it is called core-test.bartlett. And again, all you got to do is put in your PCA data frame, and it will give you this chi-square. It says your p-value is 0, but p is never actually 0. It is just less than 0.001. If it wasn't, then it would tell you. But in this case, with a chi-square of almost 10,000, that is like ultra super mega, like less than 0.001. So again, here for our KMO value is 0.85, and our p-value from Bartlett is less than 0.001.
So I think is this me talking? Yes. Okay. Cool. So if you look inside of the like help for the KMO, it says that if something is like a 0.8, it's meritorious. Is that like are the values that are under the help, is that correct? Like a KMO of greater than 0.9 is marvelous. 8 is meritorious. 7 in the 0.7s is middling. 0.6 mediocre. 0.5 miserable.
Yeah, so the conventional cutoff here for interpreting KMO is you have factorability of your data matrix, your correlation matrix, if the KMO value is above 0.6.
Okay.
So it's nice that they gave all those descriptors. They're really flowery descriptors. I've never seen anybody talk about meritorious factorability or mediocre factorability. I've always just heard it from a cutoff, like KMO above 0.6, good to go on this assumption.
They're citing in the help pane, they're citing Kaiser. So he probably from 1975. So he probably wrote it then.
Yeah. It's fine for you to use the Tabashnik and Fidel, which says the 0.6 or better. And that's not inconsistent with what Kaiser's descriptions are.
It's just less fun.
Anything that's mediocre or better is fine.
Okay.
So, and for Bartlett's test of sphericity, again, we're looking for p-values that are less than 0.001. And those two things combined tell us about the adequacy of our data for PCA or EFA. So are we ready? Oh, there's a question by Josh here. Were the correlations good? What do you guys think?
I think so.
Do we have some correlations that were above, say, 0.2, 0.3, and none that were above 0.8, 0.9?
We're talking about on the previous question, is that right?
Yeah, I think Josh was asking about the previous question of like, I'm looking at the correlation matrix, is it adequate?
Yep.
Unless you're expecting it to be a unidimensional or unifactor or one component thing, then you would expect some correlations to be 0 or even negative, because there should be subsets. So as long as you have some correlations that are overlapping in the data and you have no violations of singularity, then you're good. And thank you, Austin, for this reminder. I see it all the time in your homeworks, even though I told you on day one that it was not okay. Probability, by its very definition, can never equal 0, and it can certainly never equal less than 0. Probability can also never equal greater than 1, right? These are, by virtue of saying probability, you're saying likelihood, you're not saying certainty. So you can't have p equals 0 because that means it's a certainty, not a probability, which means you always want to write less than 0.001 or less than whatever. Okay, are we ready to move on to the next one?
All right, so number 6 is where we will do the first actual PCA analysis, and there's going to be a lot kind of coming at you here. First, we're going to use this PR comp, and I went ahead and I just already had the code in the scripts that I sent out because we're going to be using, I mean, there's a few different functions that you can do, principal components and factor analyses and stuff with R. We're mostly going to be using the principal function from the PSYC package, and over the next few labs, you'll understand why. We're starting with this PR comp function instead, and the reason that we're doing that is because for this first principal components analysis, we're basically wanting to take a direct ground up approach. We have 19 variables. We want to allow it to have 19 components. And so that we can look at that variance explained and all of these other things to get the idea for when we look across, as we talked about earlier, whether it's the theory, the Kaiser criteria, scree plot, parallel analyses, all these things. If we limit the number of components that we're allowing from the start, we can't do these things. So the first principal component analysis that we're going to do is just saying, all right, give us as many components as we have variables. And that's only done with this PR comp function. But once we get past this part and get into the other actual, all right, now we have some sort of idea about how many components we want, what types of rotations, that sort of stuff, we'll use a different function. And here, so I'm just telling it to do a principal components analysis of the PCA DF. Center equals true is just telling it to 0 center, mean center our variables, and the scale dot equals true is basically standardizing all of our different measures. So after we run that, the reason I have this here, the structure for the summary of PCA, is because if you just run summary PCA, it'll show you this, nice, pretty table, importance of components with standard deviation, proportion of variance, and cumulative proportion. But the reason that I ran the structure here is I want to show you that when you run this, this actually contains a lot of different bits of information. So when you run just summary, it looks like, oh, well, here's this thing. So if I just write, this summary as a CSV, then it'll like write out this nice little table. But that's not the case because it's only printing and showing you in the console one specific part of, which is this importance table. But it also has this thing called X, this thing called scale and center and rotation and SDev. So just wanting to point out that there's a lot of stuff within like this new PCA object that we have created that we have to go back and pull out the specific information that we're looking for. So now that we have our principal components object, this initial one. So in terms of theory.
Well, let's pause for a moment. Did everyone manage to run the PCA and then do the summary?
Yes. Not where is this? Yes.
Okay. Good, good, good. Sounds like very much yes. Okay, I'm gonna briefly, well, I assume, Austin, you're gonna briefly walk them through the summary when it comes to that part of the assignment, right?
Mm-hmm.
Okay, great. Take it away. It looks like we're all good.
All right, so let's look across all of our different ways of approaching how many components we want. And based on theory, how many components would you say we're looking at? Given the variables that we have are, what are they? The scrim 10, well, the scrim, the SE, and the depression of however many of each of those. So that said, how many theoretical components would you say there are?
3.
3. Like we would expect that there'd be one component that is depression, one component that's the discrimination, and one component that is the self-esteem. For Kaiser's criterion, remind me what that is. What is Kaiser's criterion for selecting the number of components?
You keep anything that the eigenvalue is greater than 1.
Correct. So in other words, we need to look at our eigenvalues for this PCA. One of the downsides of this PR comp function is that it doesn't just give you a straightforward, like, hey, here are the eigenvalues for this. But the PCA, this SDEV, that is the square root of the eigenvalue. In other words, if you do PCA $SDEV and then square that, it gives you, these are your eigenvalues for each of those 19 components. So the first component, the eigenvalue is 4.7. The second component, the eigenvalue is 1.94, 1.44, 1.18, 0.96. And so right there, we see that based on Kaiser's criterion, we would have how many components?
Would it be 4 components?
Correct.
Good, Nia. So quick reminder, they listed these eigenvalues in the order in which the components were extracted. And if you remember, this is a little bit like when I said how much talent is on that quiz bowl team, right? So, or who got the best plate from the buffet, the most nutritious and yummiest looking plate. So always the first component is going to have the largest eigenvalue. And in this case, it's 4.7, which means it explains by itself, that one component explains almost the same as 5 variables. It explains the same amount of variance in the original 19 variables as 4.7 x variables. Okay. So it's like it's doing a lot of heavy lifting here. Then we take what's left over, what's unexplained still, and we make a second component. And that second component had an eigenvalue of 1.94. So it explained basically like the equivalent of 2 x variables, okay? So with just the first 2 components, we already have kind of like out of 19 variables, however much variance we can explain with like almost like 7 variables, okay? That's what we mean by parsimony. The third one is the eigenvalue is going to go down. It's 1.44. The next one is 1.18. And then by the time you get to the 5th one and lower, it's explaining less variance than is contained in a single x variable. That making sense to everybody?
And then here, just to point out, like, so earlier I just ran the PCA SDEV squared to get the actual eigenvalues. But if you add in a logical test and say PCA SDEV squared is greater than 1, it will return trues and falses. And if you wrap that in sum, as far as answering the question of Kaiser's criterion and not having to actually sit and look through and count out things, just sum up that logical test, and we can now see that there are 4 eigenvalues that are greater than 1. And I know we're getting real close on time, and if somebody needs to dip out, that's fine, but I'd like to just at least get through the rest of this question to give us a good stopping point. But this is being recorded, so if you have other things to do, you know, which I don't
Like
really
go
know
back
what
to
people are doing these days, you know, maybe washing your hands obsessively or something. But anyway, so are we all good there on the eigenvalues? And again, just as a reminder that once we get to the other functions, we won't be having to like do this SDEV squared thing. That is just for this initial function that we're having to use for the bottom-up approach. So our next thing will be the scree plot. And for the scree plot, we're going to use a function from that Facto Extra package. And if you look for fviz eig, this is for visualizing our eigenvalues, and we'll tell it, we'll enter in PCA, our object, and then I'm going to add in just one additional argument, that is add labels equals true. And when we run this, we now have our scree plot, and that add labels equals true is just what actually adds on these like percentage labels, you know, where it's nice that it's showing you that percentage of variance explained. And so when we look at this now, looking at our scree plot, what is it that we're looking for in terms of determining where our cutoff should be?
We're looking for when the line drops off and goes flat.
Yeah, Casey also just typed in where it falls off the cliff.
Yeah, and so in this one, looking across this, like like a lot of things when it comes to exploratory analysis, it kind of comes down to, you know, kind of a gut feeling, because in this one, like you could make an argument for, you know, maybe 4, maybe 5, like where, I don't know, like when is it flat enough to no longer be considered dropping is a very subjective thing. So in this case, you know, we might say 4 or 5. You know, we've got different things that suggest different numbers of components here.
But would you not like say, okay, I have 3 concepts, and having more than like 4 or 5 when I'm measuring 3 would be insane anyways, unless I developed, I guess, a really bad scale?
Well, not necessarily, because the problem is that that's assuming an awful lot about the data actually lining up with your concept of this should only be 3 separate things. But in reality, if the data don't hang that way, then, you know, sure, you can force things into a scale, but it's just like if you have a 10 question scale to measure some personality trait, and if 2 of them are garbage and completely unrelated, you know, are you still going to force those items into the 10 item scale, or like do you have to say like, okay, maybe these 2 don't hang with the others the way I thought they did or thought they should. So just remember,
what if you look at your questions and component 1 makes perfect sense for one scale, component 2 makes like really good sense for the second scale, and so on, and maybe your 4th or your 5th components are like, you like read them and you're like, oh yeah, I can see where I kind of fucking blew it here.
yeah, well, and that's
going to come a little bit later, Morgan, where we're actually going to be doing that. You're exactly right. But what we're going to do is we're going to take it literally like one micro piece at a time. And so one thing I want to point out about a scree plot, because they are hard to read, is look at the line slope between the first component and the second. You know, it's a very, very steep slope, right? So clearly, like that's still going way down, okay? If you look at the slope between the second and third, so this is connecting 10.2 to 7.6, it kind of looks like this, right? Still pretty steep, like almost like a 45-degree angle. If you look at between 3 and 4, it's almost the same steepness, just a little less steep, but not very different, right? So if you were to just arbitrarily say, or not arbitrarily, but say, well, in theory, I have 3, so I'm just going to take 3, you're ignoring the fact that the data here are telling you the slope between lines 2 and 3 is like this. The slope between lines 3 and 4 is almost identical.
Yeah.
Meaning
And
I
4 and
really
5.
should take that 4th one. And even more, look at the slope between lines or its components 4 and 5. It is also, it's on, I mean, between 2 and 5 is almost a perfect straight line. So it's still falling precipitously. And it is only after you go to 5 and 6 where you really see it kind of flattening out. So if you think about it like a slope of the line between each of these pieces on a scree plot, you can say like, okay, 5 and 6, the thing gets pretty like even road. Again, like if this was a roller coaster, that's the part where we're no longer screaming and now we're like, okay, right.
Right.
And just keep in mind here that this is by definition an exploratory data approach. So we're not coming in with preconceived notions. That would be like, once we get to like confirmatory factor analysis, that's where, yeah, we think we have 3 factors here, and this is how we're going to lay them out and then test our data against some model. But in this case, we're taking a very ground up approach. So we will, by the end of this, we'll run it with 3 components. We'll run it with 4. We'll run it with 5. We'll run it with different rotations for each of these different things, and then kind of holistically say, all right, what have we gotten out of this analysis?
So Josh asked, what are the percentages?
So that is the percentage of variance explained, which we'll also get to here. And I guess we could go ahead and look at that and skip over to the parallel analysis last. So on the graph itself, so this first component explains 24.7% of the variance. The second component explains an additional 10.2%, et cetera, et cetera. And if you recall, when we ran the summary of our PCA, with this thing, one of them is like, how many components explain at least 50% of the variance. So when we look at this table here, we can see, all right, that first component explains basically 25% of the variance. That second component, it explains 10% of the variance, but cumulatively, when combined with component 1, that's up to 34.95%. Once we add in component 3 here, which explains, 7.59% of the variance, we have cumulatively now explained 42.5%. Component 4 is an additional 6% explained. That brings us up to 48.78. Component 5 is an additional 5% here, which now brings us up to 53.8% of the variance explained when we have 5 components. Is this, whenever I'm highlighting things, does that show up on y'all's screen?
Yes.
Okay, cool. Yeah, so right here with principal component number 5 is where our cumulative proportion of variance explained now exceeds 50%. So in other words, here where we say how many components do we need to explain at least 50% of our variance, in this case, we need 5.
Let me pause for a moment. And this, we might come back and do parallel analysis next time.
Yep.
When we're talking about explaining variance, I was just typing in the chat about this with Josh, who asked a question and said, what are the percentages? And you're hearing Austin and I both talk about variance explained, variance explained. Well, what the fuck variance? Which variance? What are we talking about? And what we're talking about is in all of the variables that are going into our analysis, all 19 X variables. Altogether, the 19 variables have, that's 100% of the variability in all 19 scores, okay? So when we're talking about components, we're taking a 19 items and we're reducing them down to 3, 4, 5. We're not sure how many yet. We're trying to figure out how many components or factors. But those components or factors, because we're using less than all 19, are going to not contain as much information as the original full data set. And what we want to do is we want to say, okay, we had 19 variables and altogether their variance encapsulates 100% of the variance in this data set. Now, if we take out components or factors, how much or what percentage of those data, or what percentage of that variance do those components or factors explain? We want to keep as much variance and as much explanatory variance across those fewer components or factors as we had in the original 19 variables. And one of the rules is, well, you should keep as many components or factors as it takes to explain at least half of the original variance in all of your X variables. It's kind of a dumbass rule, but it is one of the rules you'll see written. So does that make sense for everybody? And again, I explained it in the chat as well.
Yes.
Okay. We're just trying to explain the variability in all 19. Normally you're talking about variance in one variable, but in this case, we're talking about variance in all 19 variables.
All right, so we'll run the parallel analysis and then get into the other PCAs and things that we're going to do on Thursday. I was also going to mention I'm planning on putting together a brief, probably 5 to 10 minute video that uses some visualizations to kind of explain conceptually what's happening with the different rotations, that it'll be optional for everyone to watch. It helps me to not see like this whole rotation thing as being some voodoo black magic that's happening, but to actually understand mathematically what's going on is what helps it more concretely for me. So I have some graphs and stuff I've been working on. I'll try to get that up before Thursday as well. And if anybody has any questions, feel free to reach out.